Good morning. Today's my lecture topic is thermal rocket engine. The rocket principle is the basis of all propulsion in space and all launch vehicles. The twin properties of needing no external medium for the propulsion system to act conditions including the vacuum of space. The thermal rocket is the basis of all launchers and almost all space propulsion. In this, we shall treat the rocket motor as a heat engine and examine the physical principles of its operation. From these physical principles, the strengths and limitations of rocket motors can be understood. The thermal rocket motor is a heat engine. It converts the heat generated by the burning the propellants, that means fuel and oxidizer, in the combustion chamber into kinetic energy of the emerging exhaust gases. The momentum carried away by the exhaust gas provides the thrust which accelerates the rocket. As a heat engine, the rocket is no different in principle from other heat engines such as the steam engine or the internal combustion engine. The conversion of heat into work is the same whether the work is done on a piston or on a stream of exhaust gas. It will be helpful if we look first at the basic form of the thermal rocket. The basic configuration. A liquid fuel rocket engine consists of a combustion chamber into which fuel and oxygen are pumped and an expansion nozzle which converts a high pressure hot gas produced by the combustion into a high velocity exhaust stream. It is the expansion of the hot gas against the walls of the nozzle which does work and accelerates the rocket. A solid fuel motor operates in the same way except that the fuel and oxygen are pre-mixed in solid form and are contained within the same combustion chamber. Normally, the combustion takes place on the inner surface of the propellant charge. The exhaust nozzle is identical in form to that the liquid fueled motor and the principles of operation are the same. In this, we will make little distinction between the solid and liquid fueled variants of the thermal rocket motor. The combustion which takes place in the chamber can be any chemical reaction which produces heat. It may be simple oxidation of a fuel by liquid oxygen, or it may be one of a number of other kinds of exothermic chemical reaction, as for example between fuming nitric acid and hydrogen. Solid propellants may contain an oxidizer such as ammonium perchlorate together with finely divided aluminum and carbon, all bound together in a rubber-like material. Gunpowder is the classical solid propellant and was used in the first Chinese rockets. A mixture of aluminum powder and sulfur is an example of a solid propellant with no oxidizer involved. The exothermic reaction produces aluminum sulfide. The main requirement for all propellant combinations is to maximize the energy release per kilogram. Um, as with any other rocket component, the lower the mass for a given energy release, the higher will be the ultimate velocity of the vehicle. The principles of the thermal rocket do not depend on specific type of propellant, so this aspect will only impact in a minor way on the development of thrust and the effect of the atmosphere is the third law of rocket propulsion ignored the effects of atmospheric pressure and the axial forces which can be combined. The actual mass flow in the exhaust stream produces the measured thrust F equal to mv, where m is the mass flow rate and v is the effective exhaust velocity. VE combines the through exhaust velocity with the effects of atmospheric pressure and the pressure in the exhaust stream.